Remember that an important part of the CIA security triad is availability. In this context, making sure that an app is available whenever we need it, especially mission-critical apps. So what we're really talking about is a load-balanced configuration for an app. What this means is we are not only improving performance, but increasing availability. But how are we doing that exactly? Well, if we refer to our diagram, what we've got are a number of clients that need to use an app. So once we've got a load balancer configuration, the clients are not connecting directly to an application server. Instead, they're making a connection to the load balancer. So if clients are connecting, for example, to a website, that DNS name for that website needs to resolve to the IP address of the load balancer. Now, when the load balancer gets the client request for an app, depending on how it's configured, generally, it will pick from a pool of back-end servers, each of which is running the same app. It'll pick the least busy one and direct the client traffic to it. So we've got multiple back-end servers in a back-end pool then serving up the same app. So you can see now why we get a performance benefit. We've got, in our case, 3 servers doing the work for the app as opposed to just one. But also, if one of those back-end servers fails, in our configuration, we still have 2 more that are up and running and can still keep that application available to client requests. Now, what's interesting is that most load balancer configurations, and that can come in the form of a hardware appliance, or it can be a software configuration. The load balancer can use auto-scaling. Now, what that means is we might say, I want to start out with 3 back-end servers, but if the demand gets to a certain level for incoming client requests, I want to start adding additional back-end servers. Of course, those would be virtual machines. So maybe if we get to 75% of average CPU utilization for my 3 servers for 10 minutes or more, things are busy. Add another back-end server and keep doing that. That's called horizontal scaling. Actually, to be specific, it's called scaling out. You're adding virtual machine nodes to support an app. The opposite, when you start removing them because things are quieted down, that's called scaling in. But scaling out and scaling in are both examples of horizontal scaling. So now that we know a little bit about the connectivity and the data flow within a load balanced environment, let's talk about things like session persistence. You can configure your load balancer with this type of an option. And what it means is that once a client is initially directed to a back-end server behind the load balancer, it stays connected to that same back-end server for the duration of that session. Now, that may or may not be important depending on the nature of the application. So in some cases, it doesn't matter which one it keeps connecting to for a long session. In other cases, it will matter. Either way, we can enable session persistence as we see fit. Now, there are also active scheduling methods that we can configure for our load balancer. Active means that we've got multiple servers that are up and running and available at the same time. It's not like there's some servers in standby mode. No, this is active. They're all up and running and ready immediately at the same time. Now, one way that we can determine which backend server gets a client request is round robin. That means that each request that comes in through the load balancer is sent to the next server. So if the first request goes to the server 1 in the back end, the next request goes to server 2, server 3, and then back again to server 1, and so on. So we're distributing the workload in that way. That's round robin. Or we could use the least connection configuration, whereby when we get a client request, the back-end server that has the least amount of client connections gets this one because it's the least busy. We also have weighted value. Weighted value is a relative numeric value that you configure for each back-end server. So for example, if one back-end server is more powerful, maybe it would have a higher weighted value, which means it would get the lion's share or more of the client connections compared to the other servers that might be less powerful. Now, an active-passive load balancing configuration means that we have an active back-end server, but then we've got standby servers just in case, but they aren't actively involved all the time with client requests, as we just discussed with an active configuration. So this is also called a passive type of standby server configuration. So the idea is that the standby servers are there, but when are they activated? They are activated when a server that's currently designated as being active is no longer responding. Maybe it crashed, maybe it's just too overwhelmed with client connections, but that is when it gets kicked in. So when you configure a load balancer, whether it's hardware or software based, whether it's on premises or in the cloud, there are a number of options to consider depending on your specific application needs.
Now that you understand what load balancing is, there's one more important term to understand: server clustering. Let's go back to the visual. Server clustering involves linking multiple servers together to act as a single system. If one server fails, the others in the cluster can continue to operate, picking up the slack and ensuring there's no disruption. Load balancing primarily distributes incoming traffic to prevent any server from getting overwhelmed, while server clustering ensures system availability by having backup servers ready to take over in case of failures.